Welcome to the discussion. Today we're delving into the archive paper SPIRE, Synergistic Planning, Imitation, and Reinforcement for Long Horizon Manipulation. This paper tackles a significant challenge in robotics, enabling robots to perform complex, multi-step tasks. What are the core limitations of existing approaches to long-horizon robot manipulation that SPIRE aims to address?
Existing methods like pure reinforcement learning, RL, or imitation learning, IL, struggle with long horizon tasks due to the exponential increase in complexity with task length. RL requires extensive exploration, often hampered by sparse rewards, while IL is limited by the quality and scope of human demonstrations. Furthermore, both approaches face the challenge of long-term credit assignment, determining which actions contributed most to overall task success.
So SPIRE proposes a hybrid approach. Can you elaborate on the synergistic combination of planning, imitation, and reinforcement learning employed in SPIRE?
SPIRE cleverly combines task and motion planning, TAMP, with both IL and RL. TAMP decomposes the complex task into smaller, more manageable subproblems. IL is then used to train initial policies for these subproblems using human demonstrations, addressing the reward engineering problem of RL. Finally, RL fine-tunes these policies, improving robustness and performance beyond the capabilities of the demonstrations.
The paper mentions TAMP-gated learning. What does this mean and how does it contribute to the efficiency of the system?
TAMP-gated learning means that the TAMP planner decides which subproblems are best suited for learned policies, the handoff sections, and which can be handled directly by the planner. The selective application of learned policies focuses learning efforts on the most challenging aspects of the task, improving data efficiency. The planner handles simpler, more predictable actions, while the learned policies tackle the complex, contact-rich manipulations.
The paper highlights several novel strategies for training the learning agents within the planning system. Can you detail these strategies?
Yes, SPIRE employs several key innovations. First, it warm starts the RL process using the pre-trained IL policy, providing a good starting point for exploration. Second, it constrains exploration using a KL-divergence penalty, preventing the RL agent from deviating too far from the demonstrated behavior and maintaining safety. Third, it uses a multi-worker TAMP framework to parallelize planning and significantly increase the throughput of the RL training process.
The experimental results are quite impressive. Can you summarize the key performance gains achieved by SPIRE compared to existing methods?
SPIRE significantly outperforms existing hybrid learning planning approaches. It achieves a 35% to 50% improvement in average task performance, is 6 times more data efficient in terms of human demonstrations, and learns to complete tasks nearly twice as efficiently. In some cases, it successfully fine-tunes policies with initially low success rates. For example, 10% to 94%, demonstrating its robustness.
The paper mentions an ablation study removing the TAMP component. What were the key findings of this ablation?
Removing TAMP drastically reduced performance. Without TAMP's decomposition, the horizon length for the learned agent increases significantly, making both BC and RL training much more difficult. TAMP's role in breaking down the task into smaller, more manageable subproblems is crucial for SPIRE's success.
The multi-worker TAMP framework seems crucial for scalability. Can you elaborate on its benefits?
The multi-worker framework addresses 2 key issues: sample collection rate and initial state distribution. By parallelizing the planning process, it dramatically increases the number of samples collected per unit of time. The scheduler also helps manage the initial state distribution for each subproblem, ensuring that the RL agent receives a balanced and representative set of training examples.
The paper also discusses the importance of the RL divergence penalty. What role does it play in preventing undesirable behavior?
The KL-divergence penalty is crucial for maintaining safety and preventing the RL agent from diverging too far from the demonstrated behavior. In sparse reward settings, RL agents can exhibit unpredictable behavior if not constrained. The penalty ensures that the learned policy remains close to the demonstrated behavior, preventing potentially unsafe or inefficient actions.
What are some of the limitations of SPIRE, and what are potential avenues for future research?
SPIRE currently focuses on object-centric manipulation of rigid objects in tabletop environments. It also assumes the availability of human demonstrations for the learned skills. Future work could explore extending SPIRE to more complex scenarios, such as tasks involving deformable objects or unstructured environments. Investigating more sophisticated scheduling strategies and adaptive or divergence penalties could also further improve performance and robustness. Finally, exploring non-Markovian policies might enhance the model's ability to handle long-term dependencies.
The paper mentions a curriculum learning approach. How does this contribute to the training process?
The scheduler in the multi-worker framework allows for curriculum learning. The sequential strategy, for example, only allows the RL agent to train on a given subproblem once the previous subproblems have reached a certain success rate. This gradual increase in task complexity helps stabilize the training process and prevents the agent from being overwhelmed by the difficulty of the full task.
The results show SPIRE can train proficient agents with surprisingly few demonstrations. How does this compare to traditional behavior cloning?
Traditional behavior cloning often requires a large number of demonstrations, making data collection expensive and time-consuming. SPIRE's ability to train proficient agents with as few as 10 or 50 demonstrations represents a significant improvement in data efficiency, making it more practical for real-world applications.
The paper highlights a qualitative comparison showing SPIRE avoids undesirable behaviors observed in naive RL. Can you elaborate on this?
In the coffee task, for example, a naive RL agent attempted to close the lid by knocking the coffee machine, a potentially damaging action. SPIRE, constrained by the demonstrated behavior, learned to close the lid using the fingers, demonstrating a crucial advantage in safety and adherence to expected behavior.
This has been a very insightful discussion. Thank you for explaining the intricacies of SPIRE. The synergistic approach of combining TAMP, IL, and RL, along with the innovative training strategies, offers a promising path towards more robust and efficient long-horizon robot manipulation.